Thanks, everyone, for being here today. We often consider designing services to make them more resilient. But believe it or not, no matter how many checks we put in place or how often we're doing the right thing, there's going to be things that go wrong. In order to ensure that your services can handle these things that go wrong that will happen to them, we exercise resilience testing and experimentation. We talk a lot as an industry about designing for testability, and there have been a lot of good talks on that. In fact, even today at QCon. And it's not a new thing at this moment, but there are certain types of tests in experiments that are new, such as chaos experiments. And there are ways that we can design our services that will make us better prepared to participate in these kinds of resiliency tests and these kinds of resiliency experiments. In design discussions at Netflix nowadays, we've moved from what happens if this fails to what happens when this fails. The bigger the system is, the harder it's going to be to maintain, and the higher importance that's going to be placed on testability. It's no secret that Netflix's systems are heavily reliant on fallback paths. And in order to make sure these fallback paths are completing the way that we expect them to, we test them every day in the form of chaos experiments. So I want to show you one of my favorite chaos experiments here. And so this is an example of a screen that a lot of us would likely see. I'm guessing a lot of us would likely see the third row right now, the because you watch Stranger Things row. If you're still getting through Stranger Things, I totally understand if you need to dip out, and I won't look. But one of the rows that we have is the continue watching row. And say that we were running a chaos experiment for this row to make sure that, if this row failed, if we weren't able to load what you were previously watching, we wouldn't expect all of Netflix to go down, right? We would maybe expect a fallback path like this, right? We'd maybe expect just that row to not be there. We might expect to just serve something else there. But during the chaos experiment we ran to test this, we realized something like this might have happened. And because we ran a chaos experiment on it, we were able to verify that this didn't happen before customers looked at us like this. I'm Nora Jones. I'm a senior chaos engineer at Netflix, and today I'm going to talk to you about how you can design your services to participate in experiments like that, to participate in resiliency experiments, to participate in chaos experiments. And through resiliency testing, your life can be made a little bit easier. You'll get paid less, your customers will be happier, and your service will be overall more available. I work with a lot of great people at Netflix, and I'd like to thank my team for being here today, Ali, Haley, Lauren, and Casey, and letting me share this experience with you all. We also got the opportunity to participate in a book together recently. It's free on the O'Reilly website right now if you'd like to check it out, and I will have some copies of them at the Netflix reception that we're hosting on Wednesday after the conference. So let's get started. How can teams design services for resiliency testing? We're going to go through several different ways that we can make resiliency testing easier on you. So one is enabling failure injection. Another is enabling RPC, remote procedure calls. One is enabling fallback paths and having ways that we can discover them. We should enable proper monitoring and have a key business metric that we need to look for, or several key business metrics that we need to look for. And we want to have proper timeouts and ways to discover these as well. But let's take a step back for a second. There's a lot of known ways to increase confidence and resilience, like we've seen through other talks throughout the day and other things that we've practiced in managing microservices in general. So one of them is unit tests. So unit tests work like this. It's on a component level, and they're critical for verifying expected results at a very granular level. We have an input, and we verify that we get our expected output in place. And it's to validate what an individual component is doing. We also have integration tests. And integration tests work similar unit tests, and they have a similar goal, except they verify that components work well together and even services work well together. So those components working together have valid inputs and get their expected outputs, and even those services have valid inputs and get their expected outputs. Michael Bryzek said in his talk in QCon New York, he said, don't test your code locally, write an integration test to test your APIs. And if you can't write the test, then refactor your code. Deciding to trust your test is a cultural thing, and that rings so true. And I believe that's something that we really believe in here at Netflix as well. We don't just comment out our tests if they're not working properly, right? Like, that's the easy thing to do. If your tests are not working properly, you might need to make some changes in your code, right? And so that is really a cultural thing that takes place, right? You all have to believe that together, and you just kind of have to do it. And so this brings me to a point with a new way to increase confidence and resilience, and this is through chaos experimentation. So while unit testing and integration testing are valuable for identifying defects, they can miss other problems. They can miss problems that we see in production, right? With the load of production in place, with verifying that failing calls do the right thing that they're supposed to when they fail. So it's impossible to know that the system as a whole will be available and fault tolerant unless we have chaos experiments in place. So we run these in production, and they look similar to the setup as an integration test that we saw before. Except from calls from service A to service B, we can fail those in production, or we can add latency to them. Now, before I explain to you how we designed for this form of resilience experimentation, I want to explain exactly how this works at Netflix. So in order to do that, I need to show you our key business metric. And before you do chaos experiments, it's really, really important that you have a key business metric that you monitor in place. At Netflix, our key business metric is SPS, or stream starts per second, meaning how many people are actually pressing play at a given second or a given point in time. If you work at an e-commerce company, your key business metrics might be adding to cart or making sure people can check out or searching appropriately. But this is something that we really keep in place as we're doing these chaos experiments. So this is Netflix's CHAP. I want to take a quick survey first. How many people are familiar with Chaos Monkey? Wow, it's almost every hand. How many people are using some form of a Chaos Monkey in their company? Some hands. So Chaos Monkey is great, but there's a lot more failure modes that can happen other than single instance failures, right? And those are things that we should be able to verify. So in addition to Chaos Monkey, Netflix, we have a new tool called CHAP. And CHAP stands for our Chaos Automation Platform. And it works like this. So this is how traffic looks normally, right? Say we have 100% of traffic going from a service called API to a service called personalization. So we then want to make a calculation based on the amount of traffic that we have right now and relate that calculation to our key business metric. So the key business metric that I brought up to you earlier was SPS. So we've come up with a calculation at Netflix in such a way that it affects the lowest SPS possible, but still enough to give us a signal that our chaos experiment is working correctly. So based on that calculation and relating to SPS, we find a certain percentage of traffic. So say in this case, we calculated 2% of traffic, and we split that in half. And we take 1%, and we use our gateway called Zool, and we route that into a control cluster. And we don't do anything with the traffic that's going into the control cluster. We just have 1% of traffic going into the control cluster. Then we take that other 1% that we calculated, and we put it into our experiment cluster. And this is where we actually fail it or we add latency. And it's really important that we have the exact same amount in our control cluster as our experiment cluster, because we can actually monitor our key business metrics and how close they are to each other. So that key business metric SPS I brought up earlier, we actually monitor this as a part of our CHAP experiments and short it automatically if the experiment deviates too far from the control cluster. So we can add a bunch of other key metrics in there too and short them automatically based on it, or we can just fail the experiment and let it run all the way through. But the key business metric is something that we don't want the customer to have impacted. So we have that shorted automatically. And it will short whether or not it's below the control line or above the control line. Above it may be indicative of a retry storm, whereas below it may be indicative of some failures. So CHAP works on top of a service called FIT, which works. CHAP works on top of a service called FIT, and it's our failure injection testing library. And it's important in order to test for resiliency that you have failure injection testing enabled. So however your organization decides to implement failure injection testing, make sure it's easy for service owners to turn it on. So I'm going to give you all a sample failure injection library today. And this is something that I modeled off of Netflix's at a very, very high level. And it essentially allows you to fail or make a service latent. And so I'm going to go through the code with you. So this serves as a skeleton failure injection library. I built it in F# because I enjoy the succinctness of putting it on conference screens. There's not a lot of overhead with it. And I have a simple API for the library that can demonstrate its use too. So our chaos module here defines our main failure injection. We have name, which is the type of chaos we're injecting. And this is very important for logging purposes. If we want to truly remain chaotic in our approach, we could probably not allow the user to pick the chaos, but we do want to log it and have it be a parameter. Our should chaos is a Boolean. And this determines if we've met our predefined criteria to inject chaos. So this is important for safety concerns, right? So we don't want to inject chaos if our predefined criteria hasn't been met. And you want to allow service owners to decide that predefined criteria to some extent. And then chaos. In F# you can actually pass in functions as parameters to other functions, which is pretty cool. So this is the chaos function we will be injecting into our normal function. And here's our async arrow. And at a high level, the async arrow function serves as a function that produces an asynchronous computation as an output. And then the usage of the do bang here is interesting, where in most languages the bang means not. In F# it actually serves a unique purpose of asynchronous workflows, like the one in this function. So the do bang here allows us to execute this chaos parameter and allows us to enable execution on other computation threads as the chaos parameter function is being performed. So here are our two main types of chaos. We have fail with exception, right? So that could raise a random exception. And then we have introduce latency. And this has a latency parameter and allows you to put in a certain number of milliseconds that you'd like to add latency to your call. And it will sleep for that certain number of time. So then here's some sample criteria that we can do before we need to meet before injecting the chaos. And here's where it gets interesting. There's a bunch of predefined criteria you can put. You can suggest it to only do between 9 and 5. So that can be a predefined safety criteria you put. Like maybe you don't want to cause chaos after hours, right? Maybe you don't want to cause chaos when your developers aren't at work. You don't want to be mean to them. They are your coworkers, right? Don't want them to get paged more than they need to be paged. Or you can add other criteria as well. It's totally up to you. And so here's the API. So you want to make a simple enough API that your developers can use it. So A is your healthier normal function, and it gets piped with this little guy here. And it gets piped or injected with the chaos functions listed, given that the criteria that we defined before is met. So now that you have sort of a background on how failure injection testing works and how our chaos automation platform works, you kind of have an idea of where we were at a given time. So we were sitting with teams, we were sitting with service owners on a regular basis, and we were trying to come up with what made a good chaos experiment, right? And as you can imagine, that was a lot of meetings, right? And that doesn't scale. It takes a lot of effort to come up with what makes a good chaos experiment. You have to decide where to inject your failure. You have to decide if you're doing a latency experiment, how much time you want to put in there. You have to figure out what the RPC calls are. You have to figure out what the associated fallbacks are. There's a lot of stuff that goes into it, and it was very time consuming. And so we decided to start automating the creation of these. We said there has to be a better way than sitting with teams and figuring out what makes a good chaos experiment. Let's automate the creation of these. So we had to get all that stuff that I was talking about before, those RPC calls, those fallback parameters, those timeouts, retries, all that stuff, and feed it into this experiment creator. And that brings me to this point. Have good monitoring in place for configuration changes, and have good monitoring in place for your configurations. So all this stuff was in a lot of different places, right? So we're making calls out to like 5 different things right now just to get all this configuration information in one place. And now we do have it in one place, but it's very useful for performing resiliency experiments. So we also want to have RPC enabled, remote procedure calls. We needed information on remote procedure calls, whether or not these calls had associated Hystrix commands. Hystrix commands are our circuit breaker or fallback path. Whether or not those Hystrix commands had associated fallbacks with them. We needed to get timeouts. We needed to get retries. And again, we needed to have these all in one place. My colleague Lauren has this hypothesis that config changes are more dangerous than code changes. And this obviously came from something, it didn't just come from nowhere. Has anyone in here ever had a configuration change that's caused an issue for them before, surprisingly? That is almost every hand in the room, right? But we don't place a lot of monitoring on them. We don't place a lot of rules on them. Like it's kind of crazy. Some configuration files don't change. And then you kind of look at them and they haven't changed in the last 4 years, and the employee that changed them isn't even here anymore, and you're like, what do we do here, right? And so it's really important to have like good documentation around them and good monitoring around these configuration changes, and make them into an API that you could call, and you can figure out what these configurations are. So let's talk about RPC. At Netflix, our remote procedure calls are called ribbon externally. We call them NIWS internally. And they're the services we've discussed that need to talk to each other reliably with minimal interruption from the network issues, scaling events, isolated software problems, and other dangers. And this means having a valid address on the end of a REST interaction. So Ribbon is Netflix's inter-process communication, and it's built-in software load balancers. The primary model involves REST calls, and it has load balancing features, it has fault tolerance, it has multiple protocol in the form of HTTP, TCP, and UDP, and it has caching and batching. We needed to get those RPC calls, but we also needed to get their associated timeouts as well. So knowing your timeouts is very, very important for doing latency experiments, because we use this information to fuel what makes a good latency experiment and to ensure that we're running a proper latency experiment. So timeouts. When we define timeouts, we say, at what point does the service give up, right? And timeouts are really hard to figure out. They're hard to get right. A long timeout means that the node is declared dead, meaning a user has to wait, or it sees an error message, which probably isn't a good experience. And then a timeout that's too short might mean that the node is prematurely declared dead, which isn't good either. So you need something right in the middle. You need a sweet spot. And chaos experiments can actually help test for that. So retries are commonly associated with timeouts, right? immediately retrying a failure after an operation is not typically a great idea. At Netflix, we use exponential backoff on retries to avoid pulsing. But it's important for us to understand this logic. It's important for everyone to understand the underlying logic between the retries and between the timeouts and the exponential backoff, and have that logic and that information living in a place that you can easily call and access. So again, understand the logic between your timeouts and your retries. A timeout on the first attempt is likely indicative of a problem with the node, and you want to flag this as an anti-pattern. For a service behind a web API, fast enough is probably between 10 and 100 milliseconds. And beyond that, you might actually start to lose some customers and some users. So this brings me to my next point, circuit breakers or hystrix. And this was actually first introduced by Michael Nygaard in his book, Release It. And he's actually released the second version of his book, Release It 2, which is out now, and I highly recommend it. So he introduced the concept of circuit breakers and applied them to software. And so a circuit breaker exists to allow one subsystem to fail without destroying the entire system as a whole. But once the danger is past, it can reset itself and restore the full function of the program. So we apply this to software at Netflix in the form of what we call hystrix. And this is actually open sourced, and so you can access it at any point as well, as along with Ribbon, what I showed before. So traffic coming from the calling system to the service you're talking to, that traffic is monitored by the circuit breaker. And once you hit a certain error threshold, it will open, essentially, to the point where the circuit breaker opens. It no longer takes traffic. The failing service no longer takes traffic to the service that's having problems, and it can immediately return a failure or fail up the stack. And so hystrix maintains this circuit breaker functionality. So as we were gathering info for the RPC calls and for the timeouts and for the retries, we also needed to see whether or not those RPCs had hystrix commands associated with them. And in order to determine whether or not something was safe to fail, we had to ensure that it had a fallback path. And there may be times when something is still safe to fail but doesn't have necessarily a fallback in place. But this was our way of making sure that it was safe. So if your service is non-critical, I would argue that you should ensure that there are fallback paths in place. Or if you're deeming it as non-critical, meaning that it shouldn't bring your entire website down if it fails. So there's a few different fallback strategies you can have in place. Perhaps it could return a good response to the last cached value. It could return a fallback service, or it can return some sort of canned response. So maybe instead of your recommended titles, we just show you generic titles right on the screen. Instead of your recommendations showing, we show you something generic. So instead of the whole service failing, you're just not seeing it exactly as you're used to. So it's really important to know what these fallback strategies are and how to get that information. This actually relates to your business metrics so much because you should know when your critical services fail or when your not critical services fail, what's actually happening to them. And if that state changes at any given point, that should be something that you're able to consume before you're doing your resiliency tests. So we monitor our hystrix commands during our resiliency tests. We see our account successes. We see our account fallback successes. So we can actually see these during a chaos experiment that we run. And then we'll count the failures and the timeouts as well. So based on our fallback strategies and based on what we expect from a hystrix command, we can verify that this is OK during a chaos experiment by looking at these graphs. So with all that in mind, I think it's important to ensure synergy between your hystrix timeouts, your RPC timeouts, and your timeout logic, and your retry logic. They all play a huge role together. And what we found when we were gathering this info was that they were all in a lot of different places. And because they were all in a lot of different places, there were discrepancies between them, right? And so, so let's go back to CHAP for a second. We started doing all this. We started gathering all this info to feed into CHAP experiments. But as we were doing this, we realized that it wasn't all in one place. So we decided to zoom in, and we gave CHAP a monocle. So we gave CHAP the ability to have crucial optics on its services, right, and see this configuration info. So here's an example of CHAP's monocle. So this is a fake service. And we can see all this information in one place now. We started seeing really weird things based on this, right? We started seeing when Hystrix commands did not have fallbacks enabled that we thought we were supposed to have fallbacks enabled. We started seeing unwrapped RPC calls. Like, that shouldn't happen either. And then we also started seeing anti-patterns with retries on the same server. We saw Hystrix commands that were higher than the overall RPC timeouts. Timeouts that were clearly too high, timeouts that were clearly too low. And this was basically because a lot of this information was in different places, and people weren't realizing that this logic coincided with each other, right? And so we started trying to expose this, and as we saw all this information, we kind of freaked out, right? We were like, oh my gosh, what is this, right? And so we decided, I realized after seeing this, there probably isn't always money in the microservices, right? Like, it gets a little confusing after a while, right? It's a lot hard. It's very hard to keep track of all that stuff, and that's what resiliency testing is for. We can use a lot of this stuff to feed it into a prioritizer, and my colleague Haley Tucker has done a lot of work on prioritizing these chaos experiments, and she's come up with an algorithm of sorts based on this information that we found through looking for these configuration files. And so this is at a high level how the criticality score is formed, but we essentially take parts from that configuration, like maybe an RPS stats bucket, the number of retries, the number of Hystrix commands, and we weight those appropriately, and we come up with a criticality score. And based on that criticality score, we execute that chaos experiment in a certain way, right? Maybe the higher the criticality score, the sooner we run that chaos experiment. And as we're gathering more configuration information, we're getting a lot more experiments. We're getting a higher level of confidence of which experiment should be run sooner based on their criticality score, right? And so based on all this information, I want to share with y'all some chaos success stories that we've seen. And these are some of my favorite chaos success stories. So one of them was that we ran a chaos experiment which verifies that our fallback path works, and it successfully caught an issue in the fallback path, and that issue was resolved before it resulted in an availability incident. So this one was awesome, and it really demonstrated the value of the chaos automation platform. We're experimenting in production. We're experimenting on live traffic, but we have the ability to cut it off before it impacts customers, right? But we can see when it's going to cause an issue at some point down the line, and this allows us to pause and take a step back and resolve it without being under the fire of a PagerDuty alert. And here was another one of my favorite chaos success stories. It was while failing calls, we discovered an increase in license requests for the experiment cluster, even though all the fallbacks were successful. So all those graphs we were looking at earlier, they were all proving successful, but there were a bunch of increases in these requests. And that meant that whoever was consuming the fallback was retrying the call, which caused an increase in those license requests. And so Netflix engineers obviously all mean well, and we have stunning colleagues, and everyone has the best intentions, but distributed systems are inherently unreliable. That's a fact. And reliability can be built into the system, and ways to test for resiliency, saving you both time and effort instead of after the fact. And I want to do a little bit of a tangent for a second. And the reason I put those customer success stories in quotes is because we work together with the service teams to do this, right? We don't just lob things over a fence at Netflix and expect someone else to take care of our reliability and availability. It's something that we all take great pride in at Netflix and that we all work together towards. And it's because we have one goal in mind. We want our customers to have a good experience. We want We want our company's customers to have a good experience. We want Netflix to remain available and reliable. And it's important to remember that your most important customer is your actual business. And so if I can leave y'all with some takeaways from this talk, it's that designing for resiliency testing is, again, a shared responsibility. Configuration changes can and will cause outages. And it's important to have explicit monitoring in place on anti-patterns and configuration changes. That's it. If you have any questions, I will be around. Thank you.